Hey, what's up, guys? Yeah, so today I want to talk about finite field. Yeah, basically, since I already talked about some Galois theory and field extension, so I think it's very good time to discuss some finite field. But I haven't fully described the Galois theory in the full context, so I will call it finite field 1. Okay, so basically, I will prove the following results. Which is famous. Okay, so there are some results that I will prove in this video, and the first one is that given prime p. Okay, so I should say this. The first one is that all the finite field must have, let's say f, right? Must have the p to the m. So must be p is some prime, and m is some integer greater than 0. So basically, this just says that any finite field must be prime power. And the second is that there is exactly one finite field, or one finite field with order p to m. So this is basically given p to the m, there is exactly has one finite field. So everyone is isomorphic. So up to isomorphism. So this is the main thing that I plan to prove. Okay, so basically 1 and 2 characterize all finite field. Okay, so let's start. And basically, I would also talk about the idea called the splitting field. So usually, splitting field should be the thing that I described before the finite field. But I think finite field is also up to here is also can be described. And in the finite field too, after introducing the Galois theory, then I will give the so-called Frobenius group and compute the Galois group of finite extension, and also give the algebraic closure of the finite field. Okay, so these are, I think it's very classical results. Okay, so lemma. So this lemma is our key. So I should say the key. Okay, so this is the key to classify all the finite field. Okay, so let's say f is a field, and suppose you get some multiplicative subgroup. So let's say A is a f subset of f, as A is finite, and A is a multiplicative subgroup. Multiplicative. So basically, in terms of the multiple in the field f, then A will be a multiplicative subgroup, and the finite, then A is cyclic. So any multiplicative subgroup of finite field, which is finite, still must be cyclic. Okay, so this is the only non-trivial part that I think maybe in this video. So let's give the proof. So I know that A is cyclic, right? So I can write A in terms of I want to prove that A is cyclic. So I can write using the simple group theory. I know that A is a abelian group or whatever. So A is the direct sum of its zero group. So maybe, and for each hi, and which the order is pi ki. Okay, so yeah, okay, and now I can write hi in terms of let's say x belongs to G. By the way, let me just simplify notation. I use p as pi and k to be ki. Okay, so just maybe let's k to be ki. Okay, so consider is hi, right? So this x hi is x belongs to A, which satisfies x p to the j, which is 1 for some j greater or equal to 1, right? Because this HI has order p to the power, right? So it must be, or every of the element x must have some order, maximum order, such as pj is 1. Okay, and I know, and I can take, let's say, c is a maximum order, is the element between the belongs to H, has the HI has maximum order. Right, so in this case, let's say the maximum order is k. Okay, so maximum order p to a k. Okay. Okay, and but I know what? But I know that the xp to the k equals 1 has at most p to the k solution, right? Because this is in the field. Okay, so which tell me that this hi must have the order less than what? Because in this case, that let's say the maximum order is p to a k, right? So your hi of this, I should say this hi, right? This hi also every x belongs to A satisfy this hi or the solution which satisfy x to a p to a k is 1. Right? So this hi less or equal to p to a k, right? But what? But this C already generate this hi, right? Because C and the C already have so this C already have p to the k elements. So now you see the trick, right? So which tell me that the C is a generator of HI, so HI is cyclic. And since each guy is a prime power and they are coprime, so the cyclic group direct sum will be still the cyclic since they are coprime. Okay, so this is the proof. Okay, so once we have this tool that we can easily talking about the finite, we can easily classify the finite field. Okay, maybe before I talking about finite field, let me just introduce a splitting field. So let me just quickly describe the splitting fields. So definition, let's say f of f belongs to k of x, right? So somebody give you a field k, splits in a field, let's say E over k, when f of x split, right? So f of x can be written as x minus x1, x minus x2, up to x minus xn a belongs to E of x. So basically just say that a field, your E contains all the roots of the k. Okay, so generally this is or basically it's okay. So the simple way is to say that you just take E larger than let's say k of you take all the roots, right? So you can take x1, x2 and adjointed. Okay. Okay, that's it. So basically, you can view this as a splitting field, or basically any field contains k, contains the adjoint of all roots, right? So maybe that's so the theorem is that the splitting field always exists. Okay, one can try to prove this directly, but the one shortcut is that you imagine that you believe that actually one can prove that there is always algebra closure. So every polynomial at k actually can be extended, right? So you can just find something which is split in. You can find something which is split in k. Okay, but basically this will default by using called splitting field. Okay, and the splitting field are isomorphic. Okay, if you think about splitting field as it adjoining all the roots of the f. Okay, right? Because you can put f of x in terms of the k, the algebra closure, and so f of x will split in algebra closure, and you take all the roots and put in k, right? You become this. Okay, so this is the splitting field. And a quick example is that, for example, x squared minus 5x plus 6 is this. Right, so if you consider your k belongs to Q, then the splitting field will be just Q. And if you, let's say you take x squared plus 1 equals 0 in the R of x, then the splitting field will be just adjoining the roots, right? Will become a complex number. Okay. Okay, so these are all I want to say about the splitting field. Okay, so now let's talk about the originally finite field extension. Not finite field, about finite field. Okay, so let's consider this. So now we can go to a proof. Okay, so theorem that if f less than infinity, which is finite field, let's say f is Q, and suppose that f is k is a finite extension of f, and also k is less than infinity. And the number of the element in k must be Q to n. Okay, where n is the field finite field extension, right? So the order of this. So I should say kf. Okay, so this is proof. This proof. Let me just write down. So proof is trivial. The reason is that n equals to kf means that any element belongs to k can be, let's say x belongs to k, can be written as a linear combination. So that's such that a1 f1 a2 sorry a1 k1 a2 k2 an kn, right? So this ki are basis, and the ai belongs to f, right? So how many of choice of f you have, which is f, right? So x at most q to n, right? Because for each ai there's a q choice. Okay, so corollary. Now we are going to corollary 1. Corollary 1 is that if f less than infinity, then f, right? So if you have a finite field, then f has p to the m. Let's say f is a finite field, and then f has p to the m elements. Okay, so p is a prime. Okay, so proof is very simple. Using these results, I know that f has the characteristic p, right? So f has a characteristic for some prime power, for some prime, and so basically f contains a subfield generated by p. Generate a finite field with order p. So basically f contains subfield which are isomorphic to zp, or basically usually standard notation is fp. Okay, so let's say this is order n, linear, the field extension with order n, so f is p to n. Okay, so we prove that, I should say p to n, sorry. Okay, so we prove that any finite field must have the prime power, okay? So corollary 2, let's say for every a belongs to f, that a to the p to m, let's say f is p to m, must be a. Okay, so this is very important results. Okay, so proof. So we know by our lemma, if I take the multiplicative group, which is basically f delete 0, is a cyclic with order with order what? With order p to the m minus 1, right? So that means every element a belongs to f star, f multiplicative group of f must satisfy a to the p to the m minus 1 equals to 1, right? If you times a, you get a to the p to m equals to a. If a is 0, then definitely this equation is true. That's it. Okay. Corollary 3. So what? So I know that f is a, let's say f, right? Let's say f is p to m is a field, right? So that means so that means what? That means a to the p to the m equals a at most. At most have p to the m solutions. But there is equally p to m, right? So what? So that means F is a splitting field of f of p to the x, right? It's over a polynomial which is xp to the m equals to x. Okay, so this is a very non-trivial results, right? Because we already say that f has p to m, and but a to the p to m equals a, and most have p to m solutions, right? So that means this f of actually contains every roots of a to the p to m, right? So f is a splitting field of f p of x over x to the m equals to x. Okay, so which means that they are isomorphic. So what I'm saying is that I should say that every finite field have p to m is isomorphic. Okay, so there is a very simple check. So one can check that x to the p to m equals to x has no multiple roots. So that means this is the very simple idea that you should check that there is no multiple roots. And the reason is that you can just do a derivative, right? If you do a derivative, you get this, right? And this we remember that this is characteristic p, so this guy is 0, right? So -1 cannot be 0, right? So it has no multiple roots. Okay. And notice that this x to the p to m minus x, right, at most contains every solution in this, right? So this must be x minus lambda, which lambda belongs to order field f. Okay, that's it. Okay, so now let me just introduce a notation. So what we have proved is that every p to m has exactly one finite field, and it's defined to be the splitting field. Defined to be a splitting field of I should say a splitting field of fp to x over xp to m equals x. This is what I just proved. And so usually notation. So this kind of field usually use fp to m or gfp to m. This is I think due to Galois, this is a finite field. Okay, and also there is a quick exercise that you can check. Exercise is that you can check that this, I mean, one definition for quickly saying is that you can define that fp to m to be some roots. Maybe you put in a complex number or something, but let's say x satisfy xp to m equals x. And you can easily check that this is field. It is a field. This is one construction, and this construction is easy, very interesting, because you can see that if I take a plus b to the p to m will be a to the p to m plus b to the p to m, because I know that it's characteristic p, and you can also check this. Okay, so this is very interesting, but this is just one construction that you can directly check that this guy forms a field. Okay, so this is the usually construction such that every p to m has exactly one finite field, and defined to be f of p, f of x, splitting field. Basically, you take all the roots of xp to m equals x, although definitely there should be multiple of the there should be some of them. If you add join, then in the originally FP field, we give you the same, because you see there is a p to m, right? But your field only can p to m. There's no so basically some of them, let's say x equals to 0, is trivial, right? Okay, but there's a final results that I want to mention. Okay, so there's an interesting lemma that I think it would be useful in the future. So basically, if you take any finite field, and you take, let's say you take alpha and beta, which is non-zero, and both belongs to this finite field, then you can find A, B belongs to this finite field such that this 1 plus alpha A squared plus beta B squared is 0. Okay. And so this lemma will be interesting in the future. Okay, so proof. So simple case is the first case that I can consider f to be 2 to the n. Right, basically, so every element in f is basically satisfies x 2 to the n equals to x. Right, so this guy is a finite equation. So basically, it tells me that so I can write it. So basically, every element, right? So every element is a square. Right, so what I'm saying is that if you take, let's say so A1, right, any element can be written as some square. Okay. So now if this is true, then I can very easily, I can choose what? I can choose alpha. I know that alpha inverse will be some square, right? So I can choose A square such that alpha inverse is A square. And I choose B to 0. Choose B to be 0. So this equation, right, will become 1 plus alpha A square plus 0 equals to 1 plus A minus 2A squared, which is 1 plus 1 is 0. Okay. Right, because this is, remember, in the Ma2. Okay, because this has the characteristic 2. Okay. Whew. Okay, so in general, so f can be just p to the n, right? So p is some prime number which is larger or greater or equal to 3. So I can consider as w alpha, which is 1 plus alpha x squared, x belongs to f, right? And I want to count how many w alpha, right? So I need to consider alpha x squared equals to alpha y squared. So I get alpha can be it's a field, right? So x equals to plus or minus y. So basically, the number of w alpha will be 1. 1 is let's say x equals to 0, right? Equals to the pair, so x and minus x pair, right? So I get a p to n minus 1 divided by 2, right? Because minus, I already delete the identity and divided by 2 because they come in pair, right? So this is p to n plus 1 divided by 2. And then we can consider w beta, which is negative beta x squared, and x belongs to f. And the same thing, right? W of w beta has also p to n plus 1 divided by 2, right? So if you add them, you get w alpha plus w beta, which is p to n plus 1. So this tells you that which is larger than p to n, right? So that means what? That means they have some non-trivial intersection. Okay, so there is a non-trivial intersection, non-trivial element. Both non-trivial elements belongs to w alpha and belongs to w beta. Okay, so that means there exists a such that 1 plus a square alpha, right? This is in this. So let's say plug this x to be a. So 1 plus alpha a squared equals to negative beta b squared. Okay, so that's it. And yeah, this is for my finite field 1. So basically, I think the most important results is category 1 to 3. Basically, any finite field must have prime power elements, and there are splitting field, and they satisfy this equation. And this is what they are unique. Okay, so once you have this finite field idea, then you can start from here and doing some Galois. If you know about Galois theory, then you can construct many interesting things. Okay, so see you guys next videos.